On January 24th, 1986, a spacecraft did something no human-made object has ever done before or since. It flew past the ice giant Uranus, close enough to map its rings, discover new moons, and take direct measurements of its magnetic environment. Its twin, Voyager 1, launched at almost the same time, took a completely different path through the solar system, and never got anywhere near Uranus or Neptune. Only one spacecraft in the history of humanity has ever visited either of these two distant, strange, sideways spinning worlds. And to this day, nearly 40 years later, it remains the only one that ever has. What that spacecraft found seemed, at the time, straightforward enough to record and move on from. A magnetosphere almost completely empty of plasma, paired with electron radiation belts more intense than almost anything else in the solar system, second only to Jupiter's. Scientists built an entire understanding of Uranus around that single data set, including a conclusion that Uranus's 5 major moons were probably geologically dead, inert worlds with no ongoing activity at all. In November 2024, a team of researchers went back and reanalyzed that nearly 40-year-old data using tools and techniques that didn't exist in 1986, and found something that upends a significant part of what textbooks have said about Uranus ever since. The spacecraft, it turns out, may have arrived at exactly the wrong moment, catching Uranus in an extraordinarily rare temporary state that happens only a small fraction of the time. If it had shown up even a week earlier, the entire scientific picture of this planet might look completely different today. By the end of this video, you'll understand exactly what Voyager 2 actually saw, why scientists have spent decades building conclusions on top of it, and why a group of researchers now believe a huge piece of that picture was based on genuinely unlucky timing. This isn't a story built on invented urgency. The actual published research is strange enough on its own. An entire planet's scientific reputation resting for 40 years on a single flyby that new analysis suggests may have caught it in one of its rarest possible states. To understand why this reanalysis matters so much, you first need to understand exactly how unique Voyager 2's original visit to Uranus actually was, and why nothing has been able to replicate or double-check it since. Voyager 1 and Voyager 2 launched within about 2 weeks of each other in 1977, both taking advantage of a rare alignment of the outer planets that let engineers use each planet's gravity to slingshot the spacecraft further out into the solar system without burning extra fuel. Voyager 1 was sent on a trajectory specifically designed to get an especially close look at Saturn's large moon Titan, a choice that gave scientists valuable data on Titan's thick atmosphere, but which also bent Voyager 1's path up and out of the plane of the solar system entirely, permanently ending any chance of it ever reaching Uranus or Neptune. Voyager 2, following a different trajectory, kept going outward, using Saturn's gravity to redirect itself toward Uranus next. That flyby on January 24th, 1986 remains, to this day, the only time any spacecraft from Earth has ever visited Uranus up close. Voyager 2 discovered new moons, mapped previously unknown rings, and took the first, and so far only, direct measurements of the planet's magnetic environment, the invisible protective bubble of magnetic field lines that shields a planet from the constant stream of charged particles flowing outward from the sun, known as the solar wind. Earth has its own version of this same protective bubble. Without it, our atmosphere would be gradually stripped away by solar radiation over time, the way it happened to Mars billions of years ago. It's worth appreciating just how remarkable it was for a spacecraft designed in the early to mid-1970s to pull this observation off at all. By the time Voyager 2 reached Uranus in 1986, it had already been traveling through space for nearly 9 years, relying on onboard instruments and computer systems that, by modern standards, were extraordinarily primitive, decades before the kind of processing power found in even a basic modern smartphone existed. And because Uranus receives roughly 400 times less sunlight than Earth does, Voyager 2 had to operate its cameras with unusually long exposure times while still traveling at tens of thousands of kilometers per hour relative to the planet. A genuinely difficult engineering challenge that mission planners solved by carefully rotating the entire spacecraft during imaging to compensate for its own motion. That level of technical achievement, using hardware nearly a decade old by the time it reached Uranus, is part of why the data from that single flyby has been treated with such lasting scientific respect for so long. It represented an extraordinary feat of engineering, even before anyone appreciated the surprising timing quirk buried inside its results. What Voyager 2 found inside Uranus's magnetosphere immediately struck scientists as strange. Instead of the plasma, a mix of charged particles that fills the magnetospheres of essentially every other planet with one, Uranus's appeared to be almost completely empty. At the same time, its electron radiation belts, regions where energetic charged particles get trapped and concentrated along magnetic field lines, were unexpectedly intense, described by researchers as second in strength only to Jupiter's notoriously extreme radiation belts. That combination didn't make obvious physical sense. An empty magnetosphere shouldn't have anything left over to feed such powerful radiation belts in the first place. Scientists were also puzzled by a related mystery. Uranus's 5 major moons, Miranda, Ariel, Umbriel, Titania, and Oberon, are icy worlds, and other icy moons throughout the outer solar system, like Europa and Enceladus, are known to release water ions into their surrounding environment through ongoing geological activity. But Voyager 2's data showed no sign of that kind of activity around Uranus's moons at all, leading scientists to conclude, at the time, that all 5 moons must simply be geologically inert. Beyond the magnetosphere puzzle, Voyager 2's brief visit produced an enormous amount of what remains, to this day, humanity's only close-up data on this planet. It discovered 10 previously unknown moons, revealing that Uranus's family of satellites was considerably larger than anyone had realized from Earth-based observations alone. It confirmed and refined our understanding of Uranus's faint, dark ring system, first detected from the ground only 9 years earlier, in 1977. And it captured detailed images of Uranus's bizarre axial tilt. The planet is tipped over on its side by roughly 98 degrees, essentially rolling around the sun rather than spinning upright the way most other planets do. A quirk still generally attributed to a massive collision sometime in the planet's early history. Every one of these findings, alongside the magnetosphere data, has shaped scientific understanding of Uranus for the 4 decades since, simply because no other spacecraft has ever gone back to check any of it. For nearly 40 years, that single flyby has provided almost everything astronomers know firsthand about this planet. No other mission has ever gone back. In November 2024, a research team led by Jamie Jasinski, a space plasma physicist at NASA's Jet Propulsion Laboratory, published a new analysis in the journal Nature Astronomy that finally offered a compelling explanation for both of these puzzling mysteries at once: the missing plasma and the unusually intense radiation belts. Rather than only looking at the small window of data collected during the flyby itself, Jasinski's team went back through roughly 8 months of solar wind measurements that Voyager 2 had collected as it approached and passed Uranus, giving them a much broader baseline to compare the flyby moment against. What they found was striking. In the days immediately before Voyager 2's closest approach, the dynamic pressure of the solar wind hitting Uranus increased by a factor of roughly 20 compared to typical conditions. That sudden surge dramatically compressed Uranus's entire magnetosphere, shrinking it down to roughly 20% of its normal volume, from an estimated 28 times Uranus's own diameter down to about 17 times its diameter, all within about a week. To put that in perspective, imagine a planet's protective magnetic bubble, normally stretching wide enough to comfortably contain the planet, and a significant buffer zone around it suddenly getting squeezed down to a fraction of its usual size, all because of a burst of particles arriving from the sun nearly 3 billion kilometers away. According to Jasinski's analysis, when the research team checked how often solar wind conditions this extreme actually occur at Uranus's distance from the sun, they found it happens only about 4% of the time. As Jasinski put it, the flyby occurred during the maximum peak solar wind intensity across that entire 8-month stretch of data, meaning Voyager 2 didn't just happen to catch an unusual moment. It caught close to the single most extreme moment across the whole period researchers were able to examine. The team's methodology relied specifically on measurements Voyager 2 took of the solar wind's dynamic pressure, essentially a measure of how forcefully the stream of charged particles from the sun was pushing against Uranus's magnetic bubble in the hours and days leading up to the spacecraft's first crossing of Uranus's bow shock, the outer boundary where the solar wind first collides with the planet's magnetosphere. By comparing that specific window against 8 months of broader solar wind data Voyager 2 had already collected while approaching the planet, the researchers could establish a genuine statistical baseline for what normal conditions look like at Uranus, and precisely how far outside that normal range the flyby moment actually fell. That's a meaningfully more rigorous approach than earlier analyses, which had largely focused only on the data gathered during the brief flyby window itself, without the broader context needed to recognize just how unusual that specific moment really was. Adding to the complexity of understanding Uranus's magnetosphere at all is a quirk that has nothing to do with the solar wind timing issue, but makes the planet unusually difficult to interpret in the first place. Uranus's magnetic field is tilted by about 59 degrees relative to its rotational axis, and that axis itself is already tipped over by roughly 98 degrees relative to its orbital plane. That means Uranus's magnetosphere doesn't behave like a simple, steady bubble the way Earth's or Jupiter's does. It wobbles and reorients dramatically as the planet rotates, creating an already complicated, constantly shifting magnetic environment, even before factoring in a rare solar wind event. Untangling exactly how much of Voyager 2's unusual 1986 readings came from this baseline structural complexity versus how much came from the newly identified solar wind compression was part of what made this reanalysis such a genuinely difficult and valuable piece of scientific detective work. That timing has an almost uncomfortable implication built into it. Had Voyager 2 arrived at Uranus even a single week earlier, according to the research team, it would have encountered a completely different magnetospheric environment, one far closer to what scientists now believe represents Uranus's normal, typical state, rather than the extreme compressed version that ended up defining decades of scientific understanding. Here's where the story moves from simply identifying an unlucky coincidence to genuinely explaining both of the original mysteries that had puzzled scientists since 1986. According to Yashinsky and his colleagues, the intense solar wind event likely did two things simultaneously. First, the sudden compression of the magnetosphere would have physically driven much of the existing plasma out of the system, emptying it out in a way that made Uranus's magnetic environment appear starkly different from every other planet's. Second, that same compression event would have briefly intensified the internal dynamics of the magnetosphere itself, injecting additional energetic electrons into the radiation belts and supercharging them, which would explain why Voyager 2 recorded such unexpectedly powerful radiation levels at the exact same time the surrounding plasma appeared to have vanished. In other words, the two mysteries that seemed contradictory when viewed in isolation, an empty magnetosphere, somehow paired with intensely radiation-charged belts, turn out to be two sides of the very same brief, rare event. That reinterpretation carries a significant follow-on consequence for one of the other major conclusions scientists drew from the original 1986 data, the assumption that Uranus's 5 major moons must be geologically inactive. That conclusion was originally based partly on the apparent absence of water ions in the surrounding magnetosphere, which scientists took as evidence the moons weren't releasing any material into their environment the way active icy moons elsewhere in the solar system do. But if the missing plasma Voyager 2 observed was actually just a temporary side effect of an unusually intense solar wind event rather than a permanent defining feature of the Uranian system, then the absence of detected water ions during that flyby doesn't necessarily mean the moons aren't active at all. It may simply mean Voyager 2 happened to look at exactly the wrong moment to catch them in the act. As the research team has noted, this reopens a genuinely exciting possibility. Some or all of Uranus's major moons might actually be geologically active after all, potentially releasing water ions into their surrounding space in ways scientists have never had the opportunity to properly observe. That would represent a meaningful shift in how planetary scientists think about the entire Uranian moon system, moving it from confirmed geologically dead back to genuinely unknown and possibly active. A distinction that matters enormously for understanding where else in the solar system conditions capable of supporting interesting geological or even biological processes might exist. This possibility carries real weight because of what's already been learned from similar icy moons elsewhere in the solar system. Europa, one of Jupiter's large moons, and Enceladus, orbiting Saturn, have both been confirmed to have subsurface oceans of liquid water beneath their icy crusts, with Enceladus even observed venting plumes of water vapor and ice particles directly into space through cracks in its surface, a discovery that has made it one of the most closely studied targets in the search for potentially habitable environments beyond Earth. If Uranus's own icy moons turn out to share even some of these characteristics, and were simply never detected doing so because Voyager 2's one brief look happened to catch the surrounding environment in an artificially swept clean state that would meaningfully expand the list of solar system worlds worth taking seriously as potential targets for future astrobiology research. It's worth being precise about exactly what this new analysis does and does not establish. The research team isn't claiming to have directly detected evidence of active moons. They're arguing that the original evidence used to rule out that possibility was compromised by the rare timing of the flyby, which reopens the question rather than answering it definitively in either direction. As one of the researchers explained, the interpretation of Uranus's magnetosphere as uniquely extreme within the solar system may simply be an artifact of a flyby that happened to occur under unusually extreme upstream solar wind conditions, not necessarily a true representative picture of how Uranus's magnetic environment behaves most of the time. Since the study's publication, the broader planetary science community has generally received this reanalysis as a credible, well-supported piece of work, given that it was published in a peer-reviewed journal and relies on directly re-examining Voyager 2's own original instrument data rather than speculative modeling alone. That said, the researchers themselves have been careful to frame their conclusion as the most likely explanation given the available evidence, rather than an absolutely certain closed case, precisely because, without a new mission to Uranus providing independent confirmation, there's currently no way to directly verify what the planet's magnetosphere looks like under more typical conditions. The explanation fits the existing data unusually well, resolving two previously unconnected mysteries with a single underlying cause, which is exactly the kind of elegant, unifying explanation that tends to gain traction within the scientific community. But confirming it beyond reasonable doubt will likely require exactly the kind of dedicated follow-up mission that doesn't yet exist. It's worth stepping back and asking why a data reanalysis of a nearly 40-year-old flyby deserves this much attention, rather than simply being treated as an interesting historical footnote. Because for nearly 4 decades, this single, unrepeated flyby has functioned as the entire scientific foundation for how humanity understands Uranus. Every textbook description of Uranus's magnetosphere, every model of its radiation environment, every assumption about the geological state of its major moons has been built directly or indirectly on the data gathered during those few hours in January 1986. If a meaningful portion of that data reflects a rare temporary anomaly rather than Uranus's typical ordinary state, then a correspondingly meaningful portion of everything built on top of that data needs to be reconsidered, updated, or at minimum treated with appropriate caution until better information becomes available. This also matters because there's currently no way to simply go back and double-check the observation directly. No spacecraft has visited Uranus since 1986, and none is currently on its way there. NASA's 2022 Planetary Science Decadal Survey, a report produced roughly once a decade by the scientific community to set priorities for future missions, specifically recommended a dedicated Uranus orbiter and probe mission as one of NASA's next major flagship planetary science priorities, with a potential launch sometime around the early 2030s. Depending on funding and mission timelines that are still being worked out. Until a mission like that actually launches, reaches Uranus, and gathers new, independent data across a longer observing window than a single flyby ever could, this reanalysis of decades-old Voyager 2 data represents the best, most direct evidence available for understanding what Uranus's magnetosphere and moons are actually like under more typical conditions. A dedicated orbiter mission, rather than another brief flyby, would specifically address the core weakness this whole story revolves around. A single moment in time simply isn't enough to distinguish a planet's typical behavior from a rare anomaly. An orbiter could monitor Uranus's magnetosphere continuously over months or years, capturing it under a wide range of solar wind conditions, rather than whatever happened to be occurring during one brief pass. It could also directly search for water ions or other signs of activity around each of the 5 major moons individually, rather than relying on a single snapshot measurement of the broader magnetospheric environment as a proxy for what the moons themselves might be doing. That kind of sustained, direct observation is exactly what would be needed to finally settle the question this 2024 reanalysis has reopened, rather than simply reinterpreting decades-old data from a distance. There's also a broader lesson here about how planetary science works when humanity has only ever gotten one brief look at something. A single flyby captures a single moment in time, a snapshot, not a continuous record. For most solar system objects, scientists have the benefit of multiple missions, or long-term ground-based observations, to help distinguish a planet's typical behavior from a rare, temporary anomaly. Uranus, until a new mission actually arrives, doesn't have that luxury. This reanalysis is a reminder of just how much of our understanding of the outer solar system still rests on remarkably thin, single-moment evidence gathered decades ago by instruments that have long since traveled far beyond any hope of returning. So here's where this genuinely stands right now. In January 1986, Voyager 2 became the only spacecraft in history to fly past Uranus, capturing data that has defined humanity's scientific understanding of the planet for nearly 40 years, including a picture of an oddly empty magnetosphere paired with unexpectedly intense radiation belts, and a conclusion that the planet's 5 major moons were likely geologically inactive. In November 2024, a reanalysis of that same data revealed that the flyby likely occurred during an extraordinarily rare, intense solar wind event, one that occurs only about 4% of the time, which may have compressed and temporarily emptied the magnetosphere in a way that doesn't reflect Uranus's typical ordinary state at all. That reopens, without yet answering, one of the most interesting questions in this entire story. Are Uranus's moons actually active after all, quietly releasing water ions into space the way other icy moons throughout the solar system do, simply hidden from view during the one brief window humanity ever got to look? Nobody currently knows for certain. The only way to find out directly is with a new mission, one that, as of now, exists mainly as a stated priority in NASA's planning documents, with no confirmed launch date, dependent on future funding decisions that haven't yet been finalized. The real question isn't whether Uranus still holds secrets nearly 40 years after our only visit. It clearly does, An entire understanding of the planet's magnetic environment may have been built on an unlucky snapshot, and its moon's true geological state remains genuinely unresolved. The real question is whether humanity gets a second, better-timed look at this strange, sideways spinning world before too many more decades pass. If you want to be here the moment NASA's next Uranus mission gets a confirmed launch date, or when new research reveals more about what that single 1986 flyby may have missed, subscribe to the channel and turn on notifications. Because when that update comes in, we'll break it down here with the real data, not the invented version. One flyby, nearly 40 years of assumptions. A rare moment that may have rewritten a planet's story by accident. Thanks for watching.